In this video, we're going to talk about optimization, which is using the techniques of the first and second derivative test to find when something is optimal. Now, what we mean by optimal? Well, in the case of calculus, we usually mean when something is a maximum or a minimum. For instance, we might want to maximize profits or minimize the risk involved in some undertaking. So let's take a look at our first example. A farmer wishes to enclose a rectangular pen along the bank of a straight river. The side along the river requires no fencing. There are to be two partitions perpendicular to the river bank. The fencing for the partition costs $10 per meter, and the fencing for the remainder costs $20 per meter. The area of the pen must be 6,000 square meters. What outer dimensions will minimize the cost of materials? The first thing we need to do is to try to get a grasp of the information that's being presented and what's being asked. So I think the best way to start that is to sketch a picture and label the unknowns with variables. Alright, so we've got a river that has a straight bank, and we've got a rectangular region fenced in with two partitions. So this is seen from above. So there is fencing here, 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 and then in these two partitions. So there's no fencing along the river bank, and we want the area of this entire region to be 6,000 square meters, and we're trying to minimize the cost. Alright, so how do we find the cost? Well, we're given the rates cost per length for the fencing, so what we're going to need to know is how long each of these parts are. Alright, so I believe that these parts are $20 per meter. And then the two inside fences are only $10 per meter. Alright, so we're talking about a rectangle. We want to know what are the outer dimensions. Well, the dimensions of a rectangle are the length and the width. Well, it doesn't say this in the problem, but I want you to assume that the area taken up by these two partitions is negligible. It's not enough to worry about. So we're just going to think of the area of this entire rectangle as being the length times the width. Alright, so that's width, and that's the length. Alright, so once we've got our diagram drawn and we've got all of the variables in place, what we need to do is decide what it is that we're being asked to maximize or minimize. In this case, we're trying to minimize cost, the cost of the materials. So we need an equation for the thing that is being maximized or minimized. We need an equation for the cost. So let's call the cost C. Now the cost is going to be the cost of each of these fenced segments added up. So let's see, this one it costs $20 per meter and it's W meters long, so that would be a total cost of 20W. The same for this side. And then these are 10W each. This side is L meters long with a cost of $20 per meter, so its total cost is 20L. And then of course this side is free since it requires no fencing. So our cost is 60W plus 20L. Now this cost function which we have come up with, that again, that describes the quantity which is to be, in this case, minimized. The thing that is to be minimized or maximized, or that equation, is called the primary or objective equation. When you're looking for something, when you're looking for the maximum or minimum value of something, you end up taking the derivative and finding critical numbers. This is what we're going to have to differentiate. However, it's got two variables, W and L, that it depends on. We want the cost to depend on only a single variable. So in that case, where the primary equation does not depend on a single variable, we need to come up with a secondary equation, also known as a constraint equation. Now, what do we mean by a constraint? Well, what we mean is some restriction on the parameters of the problem that keep us from making, from minimizing all the way to 0. So in our case, we have to maintain an area of 6,000 square meters in this rectangular pen. If we didn't have that constraint in place, we could shrink the length and width to be 0 and have a very inexpensive pen. But let's get back to the problem at hand. Our constraint is that the area, how about we call that A, is equal to 6,000 square meters. So we need a formula for the area of this entire rectangle. Well, that would be length times width. So the length times width is 6,000. That's our constraint equation. Now what we need to do is to combine the information from this equation with the information that's in this equation. Really what we're going to want to do is solve this equation for either L or W, and it doesn't matter which. It might be easier one way than the other, but in this case I don't think it's really going to matter. I think I'll say solve it for L. So 6,000 over W is L. And now what we can do is substitute this value in for L in the original, or back in the primary equation, and we will have a primary equation that depends on only a single variable.